The topic of the webinar today is dispersion stability, redispersibility, and particle characterization, with particular focus on adjuvants, vaccines, and influenza. Please let me give you a brief introduction of our company LUM, for those who are not in touch with us, followed by some comments on the patented STEP technology we use for particle and dispersion characterization, and which forms the basis of the application examples you will see later in this webinar. Then I will have the pleasure to share with you some ideas and a case study on adjuvants characterization, as well as some information I have collected for you in terms of applications concerning vaccines and influenza. There will be a summary and an outlook. The product portfolio of instruments made by LUM has been extended from one LUMiFuge now to several instruments serving applications in the laboratory at line as well as inline to characterize particles, suspensions, emulsions, coatings, composites, and materials. Coming now to adjuvants, vaccines, and influenza. In the beginning, I would like to give you some background information, and then I'd like to share one case study with you issued by the World Health Organization, guidance on the stability evaluation of vaccines from 2006, and the more recent version has been published in 2011, the guidelines on stability evaluation of vaccines. It's a very nice and interesting document. I'd like to cite two important things from that: the real-time, real-condition stability studies on the physical, chemical, biological, biopharmaceutical, and microbiological characteristics during and up to the expected shelf life and storage periods under the expected handling and storage conditions. And only these results are to be used to recommend storage conditions and establish something related to shelf life and or release specifications. With the LUM instrumentation, we have a particular focus on the physical characteristics, and if other characteristics influence the physical characteristics, we also might detect those influences. In the WHO guidelines, they also talk about accelerated stability studies. Here I would like to underline, we talk about here the rate of change of vaccine properties over time as a consequence of the exposure to temperatures higher than those recommended for storage. That means we are not talking about physical acceleration by using relative centrifugal acceleration. We are talking here in the relation of the vaccine accelerated stability studies about higher temperature. Why do they do that? Because they say, well, if we do accelerated stability studies, it could provide already preliminary information, and later on we have to perform the real-time studies. Make a pre-selection by accelerated studies to have less samples for real-time. Coming to adjuvants, there are very many on the market, and because the case study is related to aluminum-based formulations, I have just cited here from a website about the possibilities of aluminum as an adjuvant. As we can see here, it may be in different chemical compositions like hydroxyphosphate sulfate, like hydroxide, like phosphate, or like potassium aluminum sulfate, and it is forming a part of very different vaccines against very many nasty things. And this case study is about the real-time characterization of formulations with aluminum adjuvants. So we have 3 formulations with aluminum hydroxide. 2 were loaded with a protein. It was not disclosed which kind of protein. One was characterized as a high load, sample C. Another one was characterized as a low load, sample B. And there was a sample called a placebo. This is sample A. Was the first task, is there an influence of redispersing conditions on a single sample? Are there differences due to shaking? And the second task was compare the 3 samples. Does the protein load have an influence on the sedimentation behavior? We have used the LUMiReader PSA, the real-time instrument. The SOP was programmed to record 300 transmission profiles every 5 seconds, followed by 30 profiles every 10 seconds. There was no inclination applied. Sample was in upright position. Standard light factor 1, 25 Celsius. From the range of the 3 wavelengths used for the measurement for analysis, 870 nanometers near infrared has been selected. 10 millimeter polycarbonate cells were applied for this formulation. The samples had to be stored in a fridge. They had to be warmed up to room temperature for a period of 30 minutes after removal from the fridge. The samples were tenfold shaken overhead manually with a different intensity according to the task, and in agreement with the customer, it was agreed that this procedure represents the typical future practical application. The cells were filled with a sample up to the optimum filling height using a syringe, and there was no need to use a needle because 10 millimeter cell can easily be filled. You can also use for 10 millimeter cell any kind of Eppendorf pipette or other kind of pipette. In different sedimentation results, shaken stronger means the particles sediment slower, which is typical for a flocculated sample because the stronger shaking destroys the weak flocks. Once we quantified sedimentation velocity, has been determined by using the software module front tracking. That means we follow the change of the position of the interface between the supernated and the dispersion at the value of 14% of clarification. We get the values of sedimentation velocity for the red sample, which has been redispersed softly, of 31.5 millimeters per hour. The value for the green sample is 21, so it's less than for red. Because here the flocks have been destroyed, resulting the particles are smaller. If we have Stokes' law in mind, this is clear. Smaller particles have a slower sedimentation velocity. What can we learn from that? Well, this formulation needs a very defined redispersing procedure. What can we learn from that kind of experiment? Well, there is a significant influence of the protein load on the sedimentation and on the sedimentation velocity distribution, which can easily be quantified, provided, of course, the same redispersing method is applied. So task number 1 is solved. We have detected there is an influence of the energy entry on the samples and their redispersibility, and it's easily to be quantified. Task number 2 is also solved. We have compared the 3 samples, and we can easily quantify the influence of the protein load on the redispersibility of the samples. I would like to continue now after this case study, which has been performed in-house LUM, and now on examples we have found in the literature. For any details, I always like to recommend you to contact, of course, the authors of the patent or the authors of a publication. You will find the links on the LUM website and can get in touch with these nice guys to inform yourselves. Stability studies of virus-like particles. If this is your business, you might want to know that it has been published very, very briefly in conjunction with a European project, which is called FluteCore. They use the LUMiSizer here for the stability studies. So please let me summarize now the presentation. Once we talk about the real-time characterization of adjuvants and vaccines, we always talk about the multi-wavelength separation analyzer, LUMiReader PSA, now in the most modern version 4.5.2. We can perform the real-time real-condition stability studies according to the WHO here with a focus on the physical characteristics directly, and we indirectly characterize other characteristics if those have an influence on the physical behavior. We also can perform accelerated studies according to WHO because we have a temperature range in the instrument from +4 Celsius up to +80 Celsius. Last but not least, in terms of stability studies, all samples are measured in their original concentration. And you have many more opportunities than the very few I could discuss with you today, following real-time coalescence behavior or something similar. When we talk about particle size distributions, when we talk about rapid formulation screening of adjuvants, vaccines, also applications in relation to influenza, we talk about the dispersion analyzer LUMiSizer. The most capable version is a multi-wavelength version. Here we can, as people report, determine particle size distributions, aggregate size distributions. We can perform a rapid formulation screening and selection prior to the following necessary real-time and real condition stability studies. Real-time studies would be possible, as I said, in the LUMiReader, but before we can select from 12 samples 2 or 3 for real-time. And of course, we can do the screening prior to any accelerated stability studies as demanded by the WHO. Before, we have here temperature range from +4 Celsius up to +60 Celsius. We have a focus on the physical characteristics of samples directly and monitor indirectly other kind of changes in the sample once they have influences on the physical behavior. There's a significant saving of time, space, and costs for number 2 and 3. Once we accelerate the separation, and we then, in a second step, have less formulations to be tested for many months. We measure all the samples in their original concentration. Also, the LUMiSizer has many more opportunities in the same instrument. People even reported the use of a LUMiSizer for non-destructive mechanical testing, for adhesion of particles. There's a large field. We are still at the beginning, if I may say so frankly, understanding applications in the very large field of filtration. Here we have specific filtration cells in the LUMiSizer and also some nice examples in the literature. Thank you very much for your hard work, Stefan. To you, I would like to thank you for attending this webinar. It was a pleasure for me